Okay, let's just dive right into this. If you've been paying any attention to the tech world lately, you know that AI is moving at an absolutely breakneck pace. But underneath all that software, the algorithms, the huge data centers, there is a hard physical reality that we are colliding with right now. Today's massive AI models have an insatiable appetite for memory. I mean, they're processing billions, sometimes trillions of parameters, and they have to do it instantly. The problem? Our hardware architecture is hitting a physical wall. So today, we're going to look at a totally counterintuitive, honestly brilliant engineering breakthrough that might just save the future of AI development. And that brings us to a really crucial question. What happens when AI gets too hot to think? Now, I know that sounds like a philosophical question, but trust me, it's a very real, very pressing engineering crisis. See, as we demand more and more from GPUs, the chips powering AI, we're pushing their physical materials to the absolute brink. If we can't feed data into the processor fast enough, the AI stalls. But if we push the hardware too hard using our current designs, the chips literally risk hooking themselves. To really grasp the stakes here, just listen to how researcher Hee So-young from UNST put it at the recent IEEE VLSI symposium. He said, "The size of AI models is growing explosively, but memory capacity and bandwidth are struggling to keep up, creating a massive bottleneck." So the takeaway here is that AI is evolving way faster than our hardware can physically support it. The AI brain is getting huge, but the pipes feeding it information, they're staying exactly the same size. Okay, so to understand how we fix this, we've got to look at how things currently work with HBM, or high bandwidth memory. Right now, to cram enough memory close to the processor, engineers take multiple layers of silicon DRAM dies and they stack them vertically on top of a base die, kind of like building a skyscraper. If you look at a state-of-the-art AI accelerator like the NVIDIA B300, it's flanked by 8 of these HBM stacks, with each one sitting about 12 dies high. Now, having everything this close is amazing for speed, but building straight up like a high-rise, it brings in some massive structural headaches. The way these silicon high-rises actually work is through something called TSVs, which stands for through silicon vias. You can think of these as the elevator shafts of our little skyscraper. They're vertical, microscopic connections that punch straight through every single die in the stack, carrying data and power from the bottom all the way to the top. But here's the fatal flaw with this design. As engineers try to build taller and taller stacks to hold more memory, they need to add more of these TSV elevator shafts. And every single time you add a via, you're chewing up precious silicon real estate that was supposed to be holding actual data. So the structural flaw snowballs into a critical bottleneck. Right now, standard architecture maxes out at stacking these dies 12 high. That's 12 layers of memory packed incredibly tight. But remember what we talked about earlier. GPUs generate an insane amount of heat. Experts are looking at these 12 high stacks, knowing full well we need to build them even taller for future AI, and they're honestly terrified because they're basically building a towering inferno. The root cause of this inferno really comes down to insulation. To hold these stacked dies together and protect the tiny circuits, engineers have to inject a gap-fill material between the layers. The problem is that material is incredibly thermally resistant. Actually, it's about 100 times more thermally resistant than the silicon itself. So instead of the heat flowing naturally up and out to a heatsink, it just gets completely trapped inside the stack. Imagine forcing these memory modules to run a marathon while wearing a heavy winter parka. And the result is exactly what you'd expect. Because of this thermal trap, peak chip temperatures shoot up rapidly, dangerously blowing past the 80 degrees Celsius threshold. Once you hit those temps, everything goes downhill. Performance throttles, physical materials degrade, and the risk of a catastrophic hardware failure just skyrockets. Look, you cannot run next-generation AI if your memory is melting. We need more memory, which means taller stacks. But taller stacks mean more heat and actually less storage space because of the TSVs. It's a complete engineering paradox. So what do the smartest hardware engineers in the world do when faced with an impossible vertical problem? Well, they pivot, literally. The new solution that is turning the whole industry upside down right now is to just stop stacking chips straight up and start stacking them sideways. The whole idea is to take that towering inferno of trapped heat and turn it into a cube of cool, breathable silicon fins. I know, it sounds wild, but it is an absolute stroke of genius. Let's walk through exactly how you'd build this, which experts are calling volumetric DRAM. Step 1, you actually start out the traditional way, stacking the DRAM dies vertically, one on top of the other. But then, step 2 is where the magic happens. You take that entire completed stack, and you just tip it 90 degrees on its side. Step 3, you connect that newly exposed side, which used to be the edges of the dies, directly down to the substrate. Just by flipping the orientation, you completely rewrite the thermal and structural rules of the memory module. So let's look at the first approach to this, the V-Die, South Korea's microfluidic marvel. Tipping these chips on their side creates a massive domino effect of wins. First off, because the edge of every single die is now physically touching the substrate, you don't need those vertical elevator shafts anymore. That frees up a ton of silicon to actually store data. Second, you completely eliminate the traditional base die. Instead, each individual die just gets its own input/output systems right on that bottom edge. And third, it connects to the substrate insanely tightly, every 20 micrometers. This setup gives you 4 times as many connections as standard HBM4 memory. The bandwidth potential is just staggering. But wait, it actually gets better. Remember the whole towering inferno problem? By turning the chips sideways, the researchers exposed vertical channels between the dies. This South Korean team actually used those channels for microfluidic coolant. They are literally pumping liquid coolant directly through the gaps. The result? The temperature just plummets to a remarkably chill 45 degrees Celsius. We went from a terrifying 80+ degrees down to 45. They completely solved the heat bottleneck. And the performance data absolutely proves it. The UNIS team ran a simulation using a heavy GPT-3 workload. A standard HBM4 setup pushed out about 296 tokens per second. The 16-die V-Die stack? It completely obliterated that, pumping out 540 tokens per second. Plus, it cuts read latency by 32%, which saves about 24 precious milliseconds of processing time. It's faster, it's cooler, it holds more data, it's a game changer. Now let's look at the second approach, MOSAIC, which is Japan's magnetic memory solution. To understand why Japan took a different route, we have to look at a huge physical hurdle with sideways stacking. James Myers from the research center IMEC hit the nail on the head when he said, "You have to get the thickness exactly right, or you'll miss the bond paths." Think about it. If you stack 20 dies together, and even one of them is a microscopic fraction of a millimeter thicker than the rest, when you turn the whole thing on its side, the bottom isn't going to be perfectly flat. The edges won't line up with the motherboard's electrical connections. It is an absolute integration nightmare. So the MOSAIC team came up with a fix that sounds like straight-up science fiction. Instead of relying on physical, perfect electrical connections, they use inductive coupling coils. They place these tiny coils, like 80 by 240 micrometers, on the memory dies, and matching ones on the substrate. When you run a current through one coil, it creates a magnetic field that transmits the data wirelessly across the gap. Because the data is moving via magnetic fields instead of physical pins, you get a massive amount of leeway in how perfectly that memory cube has to sit on the board. So right now, we basically have 2 totally different but completely viable philosophies for sideways memory. You've got the V-Die concept, which goes all in on direct electrical connections for raw speed and uses microfluidic liquid to aggressively cool the system. Then you have the MOSAIC concept, which uses magnetic coils so you don't need perfect physical alignment. And the crazy thing, MOSAIC doesn't even use liquid cooling. By turning the dies sideways, the silicon acts like a natural radiator. The heat just naturally drafts up through the exposed fins, naturally keeping peak temps at a safe 81.3 degrees Celsius. And because MOSAIC uses this magnetic transfer and passive cooling, they can pack the chips together incredibly tightly. By thinning the DRAM dies down to just 100 micrometers, a single MOSAIC cube could realistically hold 294 individual dies. That means one single stable cube could deliver an unbelievable 882 gigabytes of memory. Placing that kind of density right next to a GPU, that will completely change the scale of the AI models we can run. Finally, let's talk about what this all means for the future of AI hardware. We spent so much time talking about neural networks and prompt engineering, but none of that happens without the physical silicon doing the heavy lifting. To sum up what you should take away from this explainer, stacking chips sideways is the ultimate triple threat solution. First, by getting rid of those internal elevator shafts, it completely bypasses the memory capacity bottleneck. Second, by turning the chips into radiating fins, it fixes the thermal crisis that was about to melt our hardware. And third, it drastically boosts bandwidth, supercharging the speed at which LLMs generate tokens. It lets AI think faster than ever before. It really is a marvel of modern hardware engineering. Faced with an absolute physical ceiling, human ingenuity literally just turned the problem on its side. Which leaves us with one really fascinating thought to end on today. As engineers successfully flip chips sideways and master this brand new geometric puzzle, what physical dimension will they have to conquer next to keep the AI revolution growing?